Okay, let's look at some related rates. First, what we're going to do is read this problem number 2. On number 2, it tells us if the area of a circle with radius r, turns out that that area expands, find dA dt in terms of dr dt. Well, these, a and r, are our related variables. If we take a derivative with respect to time of both sides, we then get two related rates. How do we take the derivative with respect to time of pi r squared? Well, pi is a constant. It comes out here. The derivative of r squared is 2r, but then we have to do the chain rule, and we get the derivative of r with respect to time. This is just dA dt. So now we have this in terms of dr dt and other stuff. They say, suppose you got an oil spill and it spreads in a circular pattern. So we've got this, and then over time the radius gets bigger and we add more oil, right? If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meters? So if this is 1 meter per second, at the exact instant when the radius is 30 meters, if I multiply meters per second, did I do this out? If I get meters per second times a meters here, you're going to get 60 pi meters, but notice it needs to be, so this is meters per second, and this is meters, so meters times meters is where we get that meter squared. So this derivative is in meters squared per second. If we look at 4, it says the length of a rectangle. So this length is increasing at a rate of 8 centimeters every second. So if this is L, then dL dt is 8 meters per second. And its width is increasing at a rate of 3 centimeters per second. So 8 centimeters per second, and dW dt is 3 centimeters per second. They want to know how fast is the area of the rectangle increasing, so what is dA dt, when the length is 20 centimeters and the width is 10. So when the length is 20 and the width is 10. So that's why this is what our goal happens to be. So first I need a relationship that will help me relate these rates and these rates. So first I find related variables. And here I'm assuming that each one of these is a function of time. So that when I take the derivative with respect to time, none of them are constant. This is what that turns out to be, and this is the product rule. First derivative second, second derivative first, and then they tell me that this is 3 and this is 8 from the beginning, and they stop the clock when this is 10 and this is 20, so we end up getting that since this rate of change, the area is centimeters squared and time is seconds, when I multiply this out I end up getting 140 centimeters squared every second is that rate of change of the area. For 14, I read that one, a snowball is melting so that the surface area decreases at a rate of 1 centimeter squared every second. So ds dt is 1 centimeter squared every minute, What they want to know is find the rate at which the diameter is decreasing when the diameter is 10 centimeters per second. Well, diameter change would be this. When it's 10 centimeters would be written like that. So find this evaluated at 10 centimeters. So we are given that the surface area of a sphere is 4 pi r squared. Notice that's the derivative of volume, which is pretty interesting. But the radius is the same as diameter divided by 2. So d squared over 4 cancels out the 4, and this is our equation for surface area. So this is a relationship that's going to help me connect change in surface area to change in diameter. If I assume that the diameter changes with time, it's not constant, then when I take a derivative, I pull out pi. Derivative of d squared is 2d times the derivative of d with respect to time via the chain rule. And that's true, right? Well, from there, if this is true, and we knew that the surface area was changing at a rate of -1, what was it? 14. It was losing 1 centimeter squared per minute, the surface area was. So I can plug in for that. I can plug in for a diameter of 10, and that allows me to solve for the change in diameter with respect to time. End up getting -1 over 20 pi, that many centimeters per minute, is the rate of decrease of the diameter. Now here's an interesting one. Look at 16. We've got ship A. It starts out all the way over here at 150 kilometers away. Do you see it? There's 150 kilometers. Then it moves a little bit, and when it does, we stop, and its distance now is 150. Take away that x that we moved. When it moves a little further, then if I'm at this point and I started here, this distance right here is just all of 150 minus however we've gone. So when this thing makes a triangle, this down here is going to be 150 minus some distance. This is going to be a distance because this ship is moving north. And z, we're going to let be the distance between them. So at noon, ship A was going east at 35 kilometers per hour. It started 150 kilometers away. Ship B is going 25 kilometers an hour, but it's going straight north. Let's know how fast is the distance between them changing at 4 o'clock. Well, if we started at time equals 0 of noon, time equals 4 hours is 4 p.m. Oh, yeah, anyway. So if I look at this triangle, I've got 150 squared plus y squared equals z squared. That's going to relate our dy dt, dx dt, and dz dt. Again, this is what I'm wanting to know. How fast is the distance between them changing after 4 hours? So they give me this and they give me this. So when I take my derivative, the derivative of this is 2z, then chain rule gives me dz dt. Big assumption I'm making here is that x, y, and z are all functions of time. So I can take the derivative of this with respect to time, and I get 2y, chain rule gives me dy dt. And then the derivative of this, it's a function squared, so we get 2 the function times the derivative of the inside gives me negative derivative of x with respect to time, and this is what I've got. I think you'll notice that the 2's cancel out nicely when we divide both sides and we get this. And now we're ready to plug in. Remember, a big problem with these is plugging in too early. Wait till the absolute last time to plug in, because as soon as you do, we get a bunch of constants. Well, they gave us dx dt is 35. Let's see, they want to know after 4 hours. Well, let's think. After 4 hours, this has gone 25 times 4, or 100. After 4 hours, the distance that this thing has gone this way at 35 kilometers an hour, 35 times 4 is 140. So the distance that's left is 150 minus 140. So we've only got a little distance left of 10. So that means that this distance down here is just going to be 10. Right? So this is 140. So this distance right here is 150 minus x equals 150 minus 40. 140 equals 10. Right? This distance right here is 100.
So yummy. Love sugar cookies. Glad you liked it. Thank you.
So if we plug in x equal to 140 here, again, we end up getting 10. This is negative 35. This y, it's gone straight up, is 100. Dy dt is 25. And then z, if we have a 10 squared and a 100 squared, 10 squared plus 100 squared equals z squared, we get that z is root of 10,100. So z is root 10,100. When we divide, we get this, which turns out to be approximately 21.4 kilometers per hour. Pretty awesome. Notice this one is very similar. This has, we're imagining a baseball diamond where from home to first is 90. So around each one, it's like 90 feet. And so what we're going to think of is, after we've gone some distance x, what's left over is the entire distance 90 minus x. So that's why this green distance is 90 minus x. The blue is always 90 because the distance between third and first never changes. We're going to call this distance big D for distance. Okay. So we're given that dx dt, how fast I'm running, is 24 feet per second. So this is getting longer at a rate of 24 feet per second. And we want to find dd dt. Well, I've now got this triangle right here. Again, I've got 90 squared is equal to 90 squared plus 90 minus x squared is equal to d squared. So when I take the implicit derivative of both sides with respect to time, I get this. Divide both sides by 2 and I get this. But they want to know at x is equal to, it says at what rate is the distance between second base, at what rate is his distance from second base decreasing when he's halfway to first? So when he's halfway to first, x is equal to 45. Right? So I'm just doing part A. Okay. So I'm just going to do part A. I'm not going to do part B. So here, if I'm halfway, then x is equal to 45. They told me that dx dt was 24, and then I need to find d. Well, if this is 90, and I've gone 45 this way, well, 45 squared plus 90 squared equals d squared. So d is the square root of 10,125. So this goes here. And when I divide, I end up getting this, which is about 10.7 feet per second. And that's it. Hope you guys have a great rest of your day, and I'll talk to you soon.